that you flash your stimuli. And the motion onset it's a newer paradigm where you don't provide flashings, but targets can suddenly and very briefly start to move on the screen. Also, this evokes activity in the visual cortex. So these are four paradigms, and also historically grown. So this was the first, the second, the third, the fourth historically. Okay, so TVEP is the oldest paradigm. So you record it from the occipital pole, so the visual cortex, and it consists of non-overlapping flashes. So you have different targets. They flashed, but in a non-overlapping way. And as you can already guess, the timing of the flash is what discerns the different targets. That is done at a rate smaller than 4 Hertz. It will become clear why it is below 4 Hertz. And of course, your EEG equipment should be such that it is able to pick up amplitude changes in synchrony to the onsets of the flashes. So this is how it can look like. So you have flashings like that. There's only one target shown here. So each time this thing flashes, there is a particular response that is generated. And the next slide shows how it in practice looks like. So these are raw recordings. And at the vertical red line is the onset of the flash. And you see some responses here, and then you have another flash here, and another flash, another flash. And what you do, you cut out epochs in sync with the flashes, and you take it out. It looks like that. And then for the next flash, you have also that 1 second epoch you take out, and so on. So you take out all these epochs. And what you do, as you can guess, is to average them, because you can't figure out anything from the single runs here. You have to consider several runs, and then you see a particular signature that you can use in your decoder. Huh? So this is a pattern that is that you're looking for in response to a flash after averaging, of course. So you can build a template. You could use this as a template, just to screen your data at moments where you expect a flash for a particular target. And if nothing is there, then it's probably another target that you have to consider, and so on. Okay, so this is how it works. Next slide, you have, for example, 6 targets, and the flashes are occurring in non-overlapping manner. Of course, you do know when a particular target is being flashed. So as I said, you're going to apply your template to see, like, okay, assuming target 1, then I should have a match at these time here and in here and here, and for target 2 it should have a match here and here. So you can build a hypothesis, and the likelihood of your hypothesis holding, you can plot it here as another column here, and then you pick up the maximum likelihood, and this is your assumed target. And this is how it can look like. Next slide, with 6 targets. So you have your flashes running. And of course, you have to do it a couple of times to be sure that it is working properly. Okay, so wait, there is a call coming in. I hope it's not serious. Hallo? Ja, ik ben les aan het geven. Anders kan ik terugbellen. Ja, oké. Okay, look, okay, it's okay. I thought there was something wrong with my presentation. Okay, next slide is about frequency coded visual evoked potential. And here you see why I said about the 4 Hertz thingy. So this is individual flashes, the TVEP as we just discussed. You see the swing here and the amplitude. And if I repeat my flashes frequently, like 6 Hertz, so periodically, every 1/6 of a second there is a new flash, then you see that all these responses starts to add up. You get a convolved result at the end. They all are partially overlapping, and you get actually a sort of rhythmic EEG response. And if you go to 12 hertz, you see it quite clearly that there is a rhythmic response here. And different targets will have different frequencies of periodically flashing targets. So this is, of course, what you will use. If it's a 6 hertz target or a 12 hertz target or 20 hertz target, if you do a frequency analysis, you can figure out which target you're paying attention to. And this is shown in the next slide. You have 6 targets. Each one flickering at a different frequency. You analyze the EEG spectrum here, the spectrum of your EEG signal, and you look, this is the fundamental frequency here, 10 hertz, and you look like, oh, if you see that, you say, okay, you look for the target that flickered at 10 hertz, and then you have identified. You see also a harmonic here, so you have 10 hertz, but the double is there as well, and the triple as well, but you can't see it much here. So you have not only the fundamental frequency, but also the harmonics present in your EEG signal, and that has an influence in the number of targets you can place along the number of frequencies that you can have along the spectrum. Next slide shows a 2-target case. You see the flickering. So one is flickering at a higher frequency than the other. If I'm paying attention to the left one, will have a higher peak in my spectrum than when I'm paying attention to the target on the right. Okay, so indeed, the next slide shows then the spectrum here. If I'm paying attention to a 9 hertz target, then I have a peak in my spectrum at 9 hertz and the harmonic at 18, as I just explained. Or if I'm looking at the alternative target, at 10 hertz, for example, then I have that peak in my spectrum, and of course also the harmonic. So indeed, as I just said, you can have different targets with different frequencies. They need all to be placed along the spectrum, and they should not be overlapping these peaks, otherwise you can't resolve them. So you're actually more and more occupying the more targets, you have more and more peaks in your spectrum, potential peaks, and you're crowding this way your spectrum, and it has a limit. It has a limitation. Right panel shows actually that not only the frequency can be picked up, but also the phase. Suppose I have 2 targets at the same flickering at the same frequency, but with a different phase as indicated, then this is also reflected in your EEG signal. That phase, there will be a phase lag then between the EEG signal on the top line here and the bottom line. So this phase is also something that you can use, and we will come back later. Then the next slide shows an important plot from Herman and colleagues. Something it was one of the important plots that showed what the effect is of this periodic stimulation. So on the vertical axis you see the stimulation frequency going from almost 0 hertz to 100 hertz, and this is what you can pick up the horizontal scale in terms of your EEG signal, and then the diagonal here is the fundamental frequency. This is what you expect. So if I stimulate at 40 hertz, what do I see? Well, of course, always the alpha band activity around 10 hertz. You can't avoid that. You will pick that up. And then you see when it crosses the bisector, you see that you will pick up indeed also 40 hertz in your response, and you will also pick up that harmonic. And there is some other stuff here, noise, measurement noise. If I would use 20 hertz, for example, then I would pick up some subharmonic even, and around 10 hertz or so, and then the 20 hertz, and then you'll pick up the 40 hertz first harmonic, and maybe even the second harmonic at 60 hertz. So you can pick up several frequencies, and don't remind also the 50 hertz, which is the power line, will also be there. So you get this kind of spectrum when you have different stimulus frequencies. You have fundamentals, maybe even subharmonics.